yeah, with that said, I think I'm then going to continue with yesterday's work. So let us maybe just take a look at maybe another example before we move on to the next topic. Right, so just to make sure that we drive this whole thing with resistors in parallel or resistors in series home, so I'm just going to continue with this exercise we had yesterday. So I'm going to do now exercise 1.1, not 1.1, sorry, 1.2, number 8. Is the last exercise that I will do for Ohm's law. So let's quickly get that one sorted. Okay, so let's do this. Right. Okay, there we go. Error 404 on the last class. Okay, I'll see on my side if it's doing the same. So thank you for mentioning that. Let me just make a note of it real quick. And that was yesterday's class. Right, okay, so I'm going to continue with yesterday's stuff. So, okay, for this particular circuit, we're given a circuit that consists out of 3 resistors. So we have a 12 ohm, 18 ohm, and 36 ohm resistor. And yeah, they all 3 are connected in parallel with one another. So basically we have a circuit that will look something like this. Okay, so that will be something that will look like that. So there we have a 12 ohm, an 18 ohm, and a 36 ohm resistor. Right, and yeah, let me maybe do it this way. Okay, so we have those 3 resistors connected in parallel, and this combination is then connected in series with the 4th resistor. So we have another resistor here that's then connected in series, and that's an unknown resistor. So we can just call that R4. And yeah, and it is then found, okay, so basically, okay, we have that 4th resistor, and that whole circuit is then supplied with 60 volts from our supply. So we can just do a battery right here. So that will then be 60 volts. Right. Okay, so yeah, so it is then found that the power dissipated in the 12 ohm resistor is then 36 watts. So yeah, so we also have power dissipated here. Okay, so I'm going to call this resistor here R1, that one R2, and this one R3. Okay, so yeah, so that's pretty much the information that we're given here. So we need to go calculate what the value of this resistor is, and I'm not too sure if want the power dissipated by just this parallel group or all the resistors. I assume that they want the power from all the resistors, right? But we can calculate both in any case just to make sure. Right. First things first. So we need to go calculate the value of this 4th resistor. So this is a little bit tricky. So the easiest thing to do here, though, is that we can go and calculate the voltage. So we actually have enough information to calculate the voltage across the parallel section. And you can actually get enough information. We have enough information just from R1 to do, right? So we can actually go and calculate this. So if we take a look at the power calculation for R2, that will then be the parallel voltage squared divided by R, not 1. My goodness. And if we reshuffle this, that will then basically be the parallel voltage is then equal to the square root of the power times R1. That's then going to be the square root of So the power given to us here is 36 watts, and the resistance given here is 12 ohms. Okay, so that's then 12 times 36, and then we take the square root of that. And that should give us 20.785 volts for this first part. Right, so now we can actually go and calculate the voltage. So we're actually still going to need current though, if we want to calculate the resistance through that R4. But okay, but we now have enough information to be able to calculate the voltage across here. So we can actually go and do that so long, because we're going to need that voltage. That is then going to, let's see what this work out as. That's then going to be our supply voltage minus the parallel voltage, which is then going to be it's Vp. Then we fill in the numbers. That's 60 minus 20.785, which that already will give us 39.2 something. Okay, 39.215. Okay, so that's the voltage V4. And yeah, so then we can go and actually calculate the total current. But for that, we need the parallel resistance here. So if we now go calculate this parallel resistance, so we have the parallel voltage, so we can actually calculate the total current drawn using that parallel voltage and the total current drawn by these three resistors. And that will also be the same current going through R4. So yeah, so basically what we can do is we can go and calculate RP. So RP would then just be these three resistors in parallel. So there, yeah, so I'm just gonna, okay, so these are three resistors in parallel. So you can basically do 1 over RP is then 1 over R1 plus 1 over R2 plus 1 over R3. Right, so that's then 1 over RP. So yeah, so basically what we can end up with here is, yeah, so you can have, so if we simplify this to one common denominator, so that's then going to be R1 multiplied by R2. No, actually for R1, that first one, that's going to be R2 times R3, because we need to multiply with R2 and R3 there. Then that's then going to be R1 times R3 plus R1 times R2, and all of these. Oh my goodness, struggling here with, yes, okay, so all of those then divided by R1 times R2 times R3, right? Okay. Cool, so basically, yeah, so this first part you basically get, so you have to multiply with R2 and R3 at the top of the line so that you can get, yeah, so you have to, basically what you do at the bottom, you have to do at the top for each term. So in order to get R1 to be R1 times R2 times R3, we have to multiply R2 and R3 at the bottom, so we have to do the same at the top. Right, so you do that for every term, and then you end up with an equation like this. And then we can just substitute all the numbers in. So then that's going to be, what is R2? That's 18. R3, that is then 36. R1 is 12. Now we could have actually just kept it in its original form. That's fine. That's 12. What is the next one? 36. R3 is 36, yeah. Plus R1, which is 12, R2, which is 18. and then that's 12 times 18 times 36. Okay, so that's going to give us, so yeah, so you can keep it in a fraction form for now, until we convert it to the final resistance. So that's 18 times 36 plus 12 times 36 plus 12 times 18. Okay, so on top of the line, we're going to have 1,296. Here at the bottom, 7,776. So 776. Okay. So in order to get, so remember, this is still 1 over RP. We want it to be RP. So RP is then equal to 776 divided by 1296. And that will give us 6 ohms of resistance for RP. Right, so now we can actually go and calculate the total current. Okay, so the total current is going to be here. So yeah, so total current, we can actually use the parallel resistance that we calculated to do that, as well as the parallel voltage. So that's then going to be the parallel voltage divided by the parallel current, parallel resistance, sorry. So that is then going to give us, that's then 20.785 divided by 6 ohms. That will give us 3.464 amperes of current. And now we can actually go and calculate what R4's value is going to be. Okay, so now we can actually go and calculate R4. So R4, that will then just be V4 divided by the total current. So V4 we calculated to be 39.215, and dividing this by 3.464, that will then give us 11.321. And that's then in ohms. So you guys can see that actually matches quite nicely with the answer given in the textbook. Right, so the last thing that we still need to go and calculate is the power consumed by this. I think it's the total circuit. I'm not too sure if it's just the parallel resistors, but I think it's the whole circuit. So the easiest way that we can do this, we can go and calculate the total resistance, or we can actually just use the total voltage and total current. I think that would probably be the easiest way to do this. Right, so the power, so the total power, that will then be the supply voltage multiplied by the total current. Supply voltage, that is then, okay, for some reason this pen sometimes does that. And our total current, that was then 3.464. That should give you 207.84. And that's watts. Right, cool. So there's our final power calculation. Okay, everyone happy? Everyone good? Any questions? Right. So what I would advise, though, if you guys are still struggling to visualize these kind of questions, I would recommend going through exercise 1.2 near the end of this chapter. So yeah, that will actually help you guys understand these things a bit better. So yeah, so just do some practice with this. The book's name, it is on the portal as well, but I'll give it to you as well. Let me just see here if I can. Okay, so the name of the book is N4 Electrotechnics, with the author, so it's 2 authors, Tommy Ferreira and Raymond Swart. And it's the publisher is Future Managers. Right, okay, so then I'm going to continue on to the next topic. And that is resistivity. Okay, guys, so resistivity is basically an intrinsic property of a material that basically is an indication of how strongly a material will oppose the flow of electric current. So each material will have a unique resistivity associated with it. So, for instance, copper will have a different resistivity than, for instance, aluminium or iron or what some other conductors are there, gold, silver. So yeah, so resistivity, so that's a property intrinsic to your material. So the symbol for resistivity is the Greek letter rho, which looks like a lowercase p. And the unit for resistivity is ohm meters. So it's ohm multiplied by meters, basically. Right. And yeah, so if we take a look at any given material, and we take a look at the resistance will be proportional to the type of material. So this is where resistivity will come in as a property. So each material has a unique resistivity associated with it. And then it will also be proportional to the length of the material. So basically, the longer a material is, the more resistive it is. So if you think about electrical cables, for instance, so if you have electrical cable running over long distances, that cable will have a significantly higher resistance than a cable running over short distances. The resistance of a material is also inversely proportional to the cross-sectional area. So basically, what that means is that the thicker a conductor is, or the thicker the material, the lower its resistance will be. Right. So yeah, so thicker it is, the less resistance. The narrower, or the smaller. What is it? The thinner. Yeah, the thinner the conductor, the higher the resistance. Right. So yeah, so here we have a cylindrical material that actually explains it quite nicely. So the cross-sectional area is basically the area perpendicular that's going to be perpendicular to your current flow. So yeah, so there's your cross-sectional area. So that's basically the area that will be as such. And then you have your length, your resistivity, which is just a property of your material. And yeah, so basically it's then just this formula here. Now, the cross-sectional area for a circular object, so the area of a circle, that is then just pi r squared. Or you can write it as, my goodness, it's pi diameter squared over 4. So yeah, so that's both the same. Okay, so that's the cross-sectional area of a circle. If you have a square conductor, obviously not length times width. In this case, we don't have the length is the length of the conductor. Oh, my goodness, where's that eraser? The width times the height, basically. Height times width. That will then give you the cross-sectional area of a square or rectangular conductor. Okay. Right, so there are actually quite a few problems in the textbook on this as well, so I'll come back to this in a bit. So I think let's just take a look at another one here, so which is temperature coefficient of resistance. Yeah, okay, so we'll take a look at this one now as well. Okay, so for temperature coefficient of resistance, so if you guys take, for instance, any material, so basically what the temperature coefficient of resistance is a an increase in resistance per unit rise in temperature from 0 degrees C. Now, this depends. There are actually three scenarios that we actually need to look at when working with temperature coefficient of resistance. So, generally speaking, you guys will see a lot of the exercises in the textbook makes use of what we call the temperature coefficient of resistance at 0 degrees C. It can be at a different temperature as well, so then we need to account for it. But anyways, so if we take a look at a metal conductor, so most of your metal, well, pretty much all of your metals will have an increase in resistance with an increase in temperature, which means they have a positive temperature coefficient of resistance. So meaning temperature increase, resistance increase. Insulators and non-conductors typically will have a decrease in resistance with an increase in temperature, which is basically then an indication of a negative temperature coefficient of resistance. So negative temperature coefficient of resistance, increase in temperature, decrease in resistance. Right, and we can actually go and calculate the electrical resistance of a conductor at any temperature using this formula. Right, so there's another formula actually in the textbook as well. I'll go through that. Oh, maybe I can write it down here. So another formula, but there's a condition to this formula though. We can't use this formula for everything. So there's another one where it's by R1 over R2, which is then equal to 1 plus alpha naught T1 over 1 plus alpha naught T2. Right, what do you guys notice here with this formula on the right? What's the difference between the alphas? Okay, so here in this case, actually, yes, I need to change this formula. I thought I did change this, but in any case, so here, this alpha, depending, so if T naught is not equal to 0 degrees, so here alpha is at T naught. So if T naught is, let's say, at 25 degrees C, then alpha is also at 25 degrees C. Here, alpha is at 0 degrees C. Right, so that's something that we also need to take into account. I'll explain this in a moment when we do some examples on this. So so there are three situations actually that we need to consider. Actually more two, but I'll show you guys in a moment what I mean. In fact, if we go to the textbook real quick, the textbook actually explains all three cases, but I find the textbook a bit on the confusing side with this. They jump around quite a bit on this, and they're not very explicit with the formulas. Just see if I can get to the beginning of this chapter though. Let's just see here. Okay, that's all resistance. Okay, so resistivity and temperature coefficient. Okay. Right, so if we take a look here, so they actually explain it here as well. So basically they tell us here if a coil has a resistance of 1 ohms at 0 degrees C and it's heated and its resistance rises linearly as indicated by the graph in figure 1.5a, which is this figure here. If the increase in resistance for a temperature rise of 1 degree C is alpha naught ohms, then an increase for a rise of theta degree C, so theta is just the unknown degree C, is alpha times theta degree C ohms. The small increase in resistance, alpha naught, is then called the temperature coefficient of resistance at 0 degrees C. Right, so basically what we're working from here is basically an alpha naught here at 0 degrees C. Right, so that's pretty much what we have here. we do get a situation that if we don't start at 0 degrees C, then we can't use alpha naught. So that's where that other formula comes in, this one. So if we're given, so for instance, if our two resistances are at two different temperatures, like we have here, but we're given the temperature coefficient at 0 degrees C, we need to use this formula, right? We need to use this formula here. Oh yeah, so basically this formula here. On the other hand, if we have the resistance, so if we have the resistance at two different temperatures, and those temperatures are not 0 degrees C, and we're also given the temperature coefficient at the starting temperature, which is not 0 degrees C, we can use this formula. There is a mistake, however, with this formula. That minus there needs to be an equal sign. Right, so I'll go through this again in a moment. So yeah, so just keep with me here. So if our initial temperature is 0 degrees C, we can use this formula here to calculate the final resistance. Right. Okay, so yeah, so let me maybe demonstrate with an example real quick. Okay, so yeah, so let's go quickly do this. Okay, so what I'm going to do is, I think, let's do this temperature coefficient of resistance a little bit better. So I'm just going to maybe give you guys a bit of a summary here on this. Okay, so for the first case, if your maybe right here, that's your, okay, so for resistivity, no, it's not resistivity, my goodness, temperature coefficient of resistance. Okay, so if you get given alpha naught, and you get given, and your initial temperature, so, and just going to do the initial temperature is Ti equals 0 degrees C, then we can use the formula RT is equal to R naught. So R naught is the temperature at 0 degrees C. So you can actually say that's T naught. That's also fine. And then that's 1 plus alpha naught multiplied by the final temperature. So that's basically for this case. Then the second case, if alpha naught is given, and you're given a temperature that is not 0 degrees C, so your initial temperature, so T1. Okay, maybe let me keep the initial temperature T1. That's just going to make things so much easier. So if T1 is not 0 degrees C, but you're given the 0 degrees, you're given alpha naught. Alpha naught is the temperature coefficient at 0 degrees C. Right, then we use the formula of, I'm going to throw this tablet as a dead spot on it, my goodness. R1 over R2 is then equal to 1 plus alpha naught T1 over 1 plus alpha naught T2. And then the third instance, so if you are given alpha, so this is not at 0 degrees C, and you get given a temperature T1, So yeah, temperature T1, usually it will be given in some value. The textbook uses theta degrees C. I hate using this for T1. So it makes the formulas a bit weird. Anyways, so that means that I'm just gonna say T1 any temperature. Okay, no, so T1 needs to be the same temperature at alpha. Okay, so T1 at same temp as alpha. So for instance, let's say for argument's sake, so the T1 needs to be at the same temperature as alpha. So if, let's say, T1 is at 25 degrees C and you get given alpha at 25 degrees C, then you can just use this formula. So your final resistance is then your initial resistance multiplied by, and this initial resistance will also be at the same temperature as the starting temperature. Well, this is then alpha with T2 minus T1. Right. So that's the other way that you can do this. We can actually make this alpha 1 as well. Then that will be associated with T1. Okay. But this is basically the general formula, this last one. So yeah, so you can actually use this for 0 degrees C as well. It will just simplify to the first formula. Okay, everyone good so far? You guys follow what I'm doing here? So usually everyone flips out to this part. Okay, right. So yeah, so there are some conditions that we need to look at, and I'll highlight this again when we do some examples. Right. Okay, so with that said, I think let's maybe take a look at an example or two from both resistivity as well as temperature coefficient of resistance. Okay, so let's do resistivity first. I want to see if I can find one here that's... Okay, I think we can start with just start something off relatively easy. So I'm going to do exercise 1.3, number 3. Okay, so this is part of exercise 1.3 in the textbook. Okay, so let's see what we're given here. So we're given a current of 2 amps. That's then passed through a length of resistance wire of 2 meters in length and 2 millimeters squared cross-sectional area. And the resistivity of the material from which the wire is made is 420 times 10 to the minus 9 ohm meters. Right, so for 3.1, we need to go calculate the resistance of the wire, and 3.2, the power dissipated in the wire. Right, so let's just write down what we're given. So we're given the current through the wire, that is then 2 amps. We're given the length of the wire, which is 2 meters. And we're given the cross-sectional area of the wire, which is 2 millimeters squared. So we need to change this to meters squared just so that we have standard units. Now, okay, so let me maybe ask you guys here, it's a bit of a trick question. Is it times 2 to the minus 3, or 2 times 10 to the minus 3, or is it 2 times 10 to the minus 6? Oh, did I write 2 meters there for the length? It's 20, 20 meters. So for millimeters squared, guys, is it 2 times 10 to the minus 6 or 2 times 10 to the minus 3? I see Dylan here says 2 times 10 to the minus 3. Okay, I see Daniel, you say, Daniel say it's minus 6. So go on. Also says minus 6. Keegan says minus 6. Right. Let me show you guys why it is 2 times 10 to the minus 6 real quick. So so those of you that said minus 6, that is indeed the correct answer. So that's then 2 times 10 to the minus 6 meters squared. Right, so so let me maybe do it this way. Right, so view the millimeter squared as a number, right? Or millimeters as a number. So if we have millimeters squared, right? So there we have that. So if we want to change this to meters squared, we can actually just take the millimeters, view it as a single number, and then take out the square, like that. So if you use your exponential laws, that millimeter will then be millimeters squared as we had before. So millimeters, that is the same as times 10 to the minus 3 meters. So if we use our exponent, so that times 10 is basically another number, and then meters is another number. So that is then going to give us, so using our exponent laws, so basically if we have something like x to the power of y, and outside the brackets we have a z, that's the same as x to the power of yz. So you can do the same thing here. So that is then going to be, and if you have multiple numbers, so maybe let's do it with multiple numbers to show you guys what the exponent laws are. So if it's, I'm going to lose it. If it's x to the power of y, and maybe z to the power of a, let's maybe do it for argument's sake like that, and there's a b on the outside of the brackets, that's going to be the same as x, yb, z, ab. So the same thing you can do here with meter, from millimeter squared to meter squared, so that ends up being 10 to the power of minus 6 meters squared. So so when you do area, that's then going to be, so if you go from millimeter squared to meters, meter squared, that's going to be times 10 to the minus 6 and not times 10 to the minus 3, as you would do with just millimeters to meters. So keep that in mind, guys. You can do the same. You can do the same thing for volume as well. So for volume, that's obviously then going to be, so if this was 2 millimeters cubed, for instance, that would have been 2 times 10 to the minus 9 meters cubed. So so that's just something to take note of there. Okay, so what else is given to us? The resistivity of our wire. That's then going to be 420 times 10 to the minus 9 ohm meters. Right, so now we can actually go and calculate the resistance of our wire. And that will then be rho times the length over the cross-sectional area. So this is then going to be 420 times 10 to the minus 9 times 20 over 2 times 10 to the minus 6. So so this minus 6 will cancel out with that minus 9 a little bit, so that will become minus 3. And let's see here, so that 2 and the 20 can cancel out, so that will then be 10. So that will be basically 4,200 times 10 to the minus 3, which is the same as 4.2 ohms. Right, cool. Then we can go and calculate the power dissipated in the wire as well. So for 3.2, there's a problem here in the middle of my tablet. So for 3.2, that is then going to be, so the power dissipated. So we now know what the resistance of our wire is, and we know what the current through the wire is. So that's just going to be the current squared times the resistance. So the current, that is then 2 squared multiplied by 4.2. So that's basically just 4 times 4.2, which will give us 16.8. And that's watts. Cool. Right, so you guys can also get questions where you have a little bit of geometry and number of turns and things like that you also need to account for. Let me just see here. There's also another one where you guys have to calculate or use two conductors that are parallel to each other to calculate the thickness of one of the conductors. We'll do an example on that as well. Okay, so we can go, okay, so I think the next one that I'll do here is maybe either number 4 or number 6, they're very similar. Yeah, okay, I think I'm going to do number 4 and maybe then number 7 for exercise 1.3. Okay, so these exercises are all on page 46 according to Berlego. Those of you that are making use of a hard copy of the textbook, that's on page 42. Okay. Right, so in this situation, we're given a coil with 10,000 turns. So that is something that we'll need to take account of. Okay, so we have 10,000 turns of insulated copper wire. The average length per turn is 150 millimeters. So that's the average length per turn. So keep that in mind. So that is then 150 millimeters. So in this case, you can directly write it as 0.15 meters or 150 times 10 to the minus 3 meters. And then for your cross-sectional area, so that in this case is again, that's 0.3 millimeters squared. And taking this to meters squared is 0.3 times 10 to the minus 6 meters squared. Okay, so remember area, that's pretty much just the power of the 10 is double that of what you would have with the standard unit. Okay. Or what I actually meant is length. Okay, but in any case. So then we need to go calculate the resistance of the coil, assuming the resistivity of copper at a working temperature to be 0.02 microohm. Right, so we're also given the resistivity at 0.02 microohm, so that's times 10 to the minus 6 ohm meters. Right, okay, so now we need to go calculate the resistance. Okay, so you can do this in one of two ways. Right, so you can either do it this way. You can calculate the resistance for one turn, basically, and then multiply it with the number of turns. You can do it that way around, or you can just calculate the total length of the coil in the beginning, which is what I'm going to do. Okay, so we can calculate the length, so the total length. That will be your length per turn, multiplied by the number of turns. So that's then going to be 0.15 meters times 10,000. So that's basically going to be 1, 2, 3, 4. And that's going to be, maybe let me calculate this like this, otherwise. That's 0.15 times 10,000. So that will give you 1,500 meters of copper wire. So that means then we can then just use so we already multiplied this here, so then that's then rho times the total length over that. So that's the second way, the other way that you could have done it, or the other way that we can do it, which is the one that I'm taking here. That is in 0.02 for the resistivity times 10 to the minus 6, and the length being 1,500, and divided by 0.3 times 10 to the minus 6. Right, so those two will cancel out. And that's 0.02 times 1,500 divided by 1.3. And that will give us 100 ohms for this coil. Right. Cool. Everyone happy so far? Everyone good? Okay, so as you guys can see, you just need to keep the number of turns in mind here with this exercise. Okay, so let's go take a look at same exercise 1.3, but number 7. Okay, so this one, we have two wires. Okay, so we have an aluminium wire that is 7.5 meters long. It is connected in parallel with a copper wire that is 6 meters long. Right. And then we are told when a current of 5 amps is passed through the combination, so that means the total current is 5 amps. It is found that the current through the aluminium wire is 3 amps. So that means the other remaining 2 amps is then flowing through the copper wire. Okay, so the diameter of the aluminium wire is 1 millimeter, and we need to go determine the diameter of the copper wire. Now we're given the resistivity of the copper, which is 0.017 micro-ohm meters, and we're given the resistivity of aluminium, which is 0.028 micro-ohm meters. Right. Okay. So I just want to start off that this is a question that is common enough in the exams that you guys stand a really good chance to get a question like this. And yeah, so you might also get one in the test, you might not, who knows. So I would recommend you guys pay attention to how this one is solved. Right, so let's start off with what's given to us. So I'm going to kind of write the copper stuff in a different color to the aluminium stuff. Right, so for the copper, so if we take here the copper, so I'm just going to call that LC, that is then 6 meters. Yeah, so then we have a total current of 5 amps. I'll write that down in a moment. Current through the aluminium wire, diameter of the aluminium is 1 millimeter. Determine the diameter of the copper wire. So we want to know what the diameter of the copper wire is. And we've also given the resistivity of copper, which is 0.017 micro-ohm meters. So that's times 10 to the minus 6 ohm meters. And yeah, so there's the information that we have for the copper. And then for the aluminium, so the length of the aluminium, that is then 7.5 meters. The current, okay, total current is 5 amps. The current through the aluminium wire, that is then 3 amps. The diameter of the aluminium wire, that's then 1 millimeters. And the resistivity of the aluminium wire, that is then 0.028 times 10 to the minus 6 ohm meters. Right. Let me just write down the total current here as well. 5 amps. Right. So we can actually go. Right, so one of the things that we can do is, okay, so I don't know if you guys can see, we don't have enough information really to go and calculate what the diameter of the copper conductor is. Or we can't do it straight off the bat. There's still some values that we need. So we can, yeah, so for a start, we're going to need the resistance of the copper wire, which we don't have. And we can actually go and calculate it. We just need the voltage across the parallel combination and the current through the copper wire. Right, so the current through the copper wire, that's actually quite easy to calculate. That will just be the total current minus the current through the aluminium conductor. And that's then going to give you 5 amps minus 3 amps, and that's then 2 amps for that current. And yeah, so the next step that we will have here is that we need to go calculate what the resistance of the aluminium conductor is. We have enough information for the aluminium conductor to calculate its resistance. And yeah, and we can use that resistance to calculate the voltage across that parallel combination, and thus then calculate the resistance of the copper conductor and use that value then to calculate the diameter of the copper conductor. Right, so I just want to reiterate here is that the area of a circle is equal to pi times the diameter squared over 4. So we can actually substitute this in our equation. So I'm going to calculate the resistance of the aluminium conductor here. So that is then going to be rho times L over A. So if we substitute the area here with pi d squared over 4, that's then going to result in basically 4 multiplied by rho times L over pi times, okay, but this is all the aluminium values, pi times dA squared. Right. Okay, so remember 1 millimeter, this is then going to be 1 times 10 to the minus 3 that we have there. Okay, so that d squared is actually going to make it 1 times 10 to the minus 6. Okay. Okay, that's then going to be 4 multiplied by the, what is it, the resistivity of the aluminium. Okay, that's what we have there. The length of the aluminium, which is 7.5 meters. And this whole thing, oh my goodness, this whole thing divided by pi multiplied by 1 times 10 to the minus 3 to the power of 6, 6 squared. Okay, so basically if you square this 1 times 10 to the minus 3 out, that's then going to be times 10 to the minus 6. So basically this and this is then going to cancel each other. So that then becomes 1 to the, 1 squared, which is just 1. So we end up with 4 times 0.028 times 7.5 divided by pi. Right, so this will give us a resistance of 0.267 ohms. Okay, so that's the resistance of the aluminium conductor. Right, so now we can actually go and calculate the voltage drop across that parallel combination because we know what the current through the aluminium conductor is and we know what the resistance of the aluminium conductor is now. Okay, so the voltage then, that will then be equal to the current through the aluminium conductor multiplied by the resistance of the aluminium conductor using Ohm's law here. Okay, so the so this is then 3 amps multiplied by 0.267. Okay, and this is then going to give us a voltage of 0.801 volts. Okay, so using this voltage, we can actually calculate the resistance of the copper conductor. So that is then going to be the voltage divided by the current through the copper conductor. So remember, these two conductors are connected in parallel. So that's then going to be 0.801 divided by 2. So yeah, so this is going to be 0.4005 ohms. You can round it to 0.401 if you want to. I'm just going to keep it this way just to kind of keep our calculations as accurate as possible, or as precise as possible. So yeah, so that's the copper conductor's resistance. Okay, So, but you can also calculate the resistance, or rather, let me write the formula down using the resistivity. So yeah, so remember this is also a round conductor. So whenever you see the word diameter, your mind needs to go to a circle, as in immediately you see the word diameter. And then if we reshuffle this equation, that will then just be 4 rho C LC over pi RC. And then okay, so when we substitute all these values, that's then going to be 4 multiplied by, I believe this was what, 0.017 times 10 to the minus 6. The length was 6.5 meters, if I remember correctly, or it was just 6 meters, not 6.5. And that is then pi, and RC, we calculated as 0.4005. Okay, so that's 4 times 0.017 times 6 divided by a million divided by pi divided by 0.400775, I mean, and then this, taking the square root of that. Okay, so what I'm getting for the diameter of the copper conductor is 0.569 millimeters. If we take a look at the exercise here, yeah, so that's also what they're calculating, 0.569 millimeters for the copper conductor. Okay. Okay, everyone good so far? Okay, awesome. Yeah, so I think, yeah, so this is pretty much the, how can I put this? This is pretty much the most difficult that the resistivity calculations can get, is with this layout, or with this kind of question. And they regularly ask this kind of question in the exams. But something that will, yeah, so with a little bit of variation on it. So maybe they'll give you different lengths. So I know one of the questions that they usually have is that the one conductor is 150 meters long, the other one is 100 meters long, with different currents as well. And then obviously that's going to result in different voltage drops different voltage drop across the conductors as well. So yeah, guys, yeah, so this is, you have a pretty good chance of getting this in the exams. Right, cool. All right, guys, I don't think I'm going to start with new work or continue with another example. I actually want to do temperature coefficient of resistance as well. I'll start off tomorrow with that, with an example of that, and then we will continue with new work. Right, guys. Then, yeah, I will put today's slides with the annotations on as well. Maybe let me do the screen sharing here as well to, where is that stuff? Yeah, the temperature coefficient of resistance, the different situations where it can be used. So those of you that still want to write this down or take a screenshot or whatever, guys are welcome to do so. And then let's just quickly do this. Okay, cool. There it is. Okay, so that's for today's work. Okay, guys. Then, yeah, then that's that. Okay, guys, then I'll see you guys tomorrow. Cheers. Have a great afternoon.
Thank you very much, sir. Have a good afternoon.
Thank you.